Okay, let's dive in. Think about this. What if we could unlock a whole new level for electric cars? Get more range, make them lighter, maybe even bring the cost down a bit.
All by rethinking something as basic as the electric motor itself.
Exactly. And that's what we're digging into today. We've waded through a whole stack of sources, articles, research notes, some videos too, all focused on this German startup, DeepDrive.
Right, DeepDrive. And their electric motor tech, which looks potentially, well, game-changing.
So our mission for this deep dive, figure out what's so special about this dual rotor motor they've developed, understand the kind of ripple effects it could have for EVs.
And crucially, get a grip on the real-world side. Like, who's actually backing this? When could you maybe see one in a car?
Let's get right to the core concept then. What makes this deep drive motor fundamentally different?
Okay, so it's a totally different motor architecture. The simplest way to picture it is maybe fitting the work of two electric motors into the space of roughly one, but like in a completely new way.
Right, because usually an EV motor has the stationary part, the stator with the coils,
Yeah,
and that drives the spinning part, the rotor. And in most motors now, the stator is either pushing a rotor inside it or sometimes one wrapped around the outside, one or the other.
exactly. But what DeepDrive did, their innovation, is use a single stator right in the middle. And that one stator drives both an inner rotor and an outer rotor simultaneously.
Ah, okay. So both spinning parts get energy from that same static core.
Precisely.
The sources call it a double rotor radial flux machine. Radial flux sounds technical, but that just means the magnetic forces work perpendicular to the axle, right? Which is pretty standard efficient design.
Yeah, that part's normal. It's the double rotor bit that's the real twist here.
And apparently it's that double rotor setup powered by one stator that unlocks all these benefits we were talking about.
That seems to be the key. Yeah, it leads to this whole cascade of advantages.
Okay, let's break down those benefits then. Why should you, listening now, care about this? First up, the big one, efficiency and range.
This is probably DeepDrive's headline claim. They're saying this design can improve the overall drivetrain efficiency by, well, a pretty significant amount. The figure they put out is around 20%.
20%, wow. That's not a tiny adjustment.
No, it's substantial.
And if you think about range, a 20% efficiency boost, that could genuinely push EVs towards, or maybe even past, that 800-kilometer mark on one charge.
Yeah, over 500 miles. That's huge for anyone worried about range.
Definitely.
But what's really interesting, and that sources dig into this, is how they get that efficiency. They point out, the peak efficiency of a good EV motor is already super high, like 96%, maybe more.
Right. So the real gains aren't just squeezing another percent out of the motor at its absolute best.
Exactly. It's about the whole system.
Yeah.
The well-to-wheel efficiency, as they call it. It's all the energy you lose getting power from the battery, through the electronics, the inverter, the motor itself, maybe a gearbox, and then finally, to the wheels.
Okay, so minimizing losses along that whole chain.
Precisely. And the sources, they give this comparison using a Tesla Model 3. Now, they do note it's not the newest model today, but it's a good benchmark people know.
Sure.
So in a conventional setup like that, you might lose something like 3.5 to 4 kilowatt hours for every 100 kilometers you drive. Just wasted as heat, mostly.
Okay, 3.5 to 4 kilowatt hours lost per 100 kilometers. And DeepDrive, especially with their wheel hub motor versions, they think they can cut that way down.
That's the claim. They project that for the same 100 kilometers, the loss could be down around 1.5 kilowatt hours.
Wow, so cutting the energy wasted in the drivetrain by potentially more than half?
Yeah, that's the idea. And that's where the big range increase comes from. It's not just tweaking the motor's peak efficiency by a tiny bit.
That makes sense. Though, like you said, the sources are careful. These are company figures for now.
Absolutely. They need that independent real-world testing once the tech is actually out there. Validation is key.
Definitely. But still, the potential numbers are, well, really compelling. Okay, so beyond using less energy, what's next? Size and weight seem to be another major plus.
Yeah, the dual rotor thing lets them pack a lot of power and torque into something that's like remarkably small and light compared to traditional motors with the same output.
And the sources actually put a number on the weight saving for the whole vehicle, right? Up to 150 kilograms?
That's 150 kilos, yeah.
Yeah.
That's significant. It's like kicking 2 average adults out of the car.
Huh. Okay, good way to put it.
And saving that kind of weight and space, it gives car designers a ton of flexibility.
Yeah.
You can maybe put these motors right in the wheels themselves.
Uh-huh.
We'll talk more about that.
Right.
Or even if you use a central motor version, just the fact that it's smaller frees up space inside the car, maybe for a bigger battery, push the range even more, or just give people more legroom or luggage space.
So better range, less weight, more space potential. But are they sacrificing power to get that small size?
Doesn't seem like it, according to the
Yeah.
reports. They talk about some pretty impressive torque figures. Some versions capable of up to 3,400 Newton meters.
3,400 meters. That's serious grunt. That means quick acceleration, responsive driving.
Definitely.
How does having that second rotor actually help generate so much torque? Is it just like adding a whole second motor's torque?
It's apparently more clever than that. The sources explain that the outer rotor, specifically, adds a substantial chunk of extra torque,
Mhm.
something like 30% more than if you just had the inner rotor in the same design.
Oh, okay.
Having that second surface interacting with the stator's magnetic field lets them sort of leverage the forces more effectively in that compact space.
Okay, this is sounding pretty good. More efficient, lighter, smaller, and powerful. Ticks a lot of boxes for EVs. What about the materials? That's such a huge topic now. Rare earths, costs, supply chains.
Yeah, and this is where deep drive tackles a really critical issue for the whole industry. And honestly, it's a strategic one, especially for Europe. Their design uses way fewer rare earth materials
Okay.
and less iron and magnet material overall, too. The sources actually put numbers on it,
Mm.
potentially half the magnets
Mhm.
and saving up to 80% of the iron and magnet material compared to some traditional motor designs.
Whoa, half the magnets, 80% less iron and magnet material. That's huge. Why is cutting down rare earths so important strategically?
Well, it boils down to a few things: cost, supply stability, and, frankly, geopolitics. Rare earths are key for the strong magnets in many powerful EV motors, but they're expensive.
Right.
Getting them out of the ground can be environmentally tough, and the global supply is heavily concentrated in just one region, mainly China. So reducing reliance on them is massive for controlling costs long term.
And for sustainability and just having a more secure supply chain, right? More European autonomy in making EVs.
Exactly that. It's not just about making the motor itself cheaper to build, it's about lessening a strategic vulnerability for the whole sector.
Makes sense. Though the sources did point out they reduce rare earth use, they don't eliminate it entirely yet.
Correct. It's a reduction, not zero rare earths. And it's also worth noting, DeepDrive isn't the only one working on this problem. The sources mention others trying different angles, like Green Silence Group's Spinroll Tech, or even using AI to design new magnets like that Magnex project. It just shows this whole area, reducing or ditching rare earths, is a major focus for innovation right now. Lots of competition driving things forward.
That's fascinating context. So DeepDrive is part of this bigger push for more sustainable, more secure motor materials. Okay, one more point they mentioned was versatility.
Yes, the core tech seems flexible. It can be used in two main setups: either a more traditional central motor that drives the wheels through axles, like most EVs today,
Okay.
or the more radical approach, a decentralized system with the motors built right into the wheel hubs.
Right. Let's dig into that wheel hub idea a bit more
Yeah.
because putting the motor in the wheel, it sounds futuristic, but you mentioned it's actually quite an old concept.
It really is. Ferdinand Porsche, believe it or not, showed off a car with electric motors in each wheel hub way back in 1900.
1900. Wow.
Yeah. So the idea itself isn't new at all, but having the materials, the control systems to make it work well for a modern high-performance EV, that's much more recent.
And the theoretical advantages are obvious, aren't they? You free up all that central space in the car
Totally.
and you simplify the drivetrain, right? Power goes straight to the wheel, fewer mechanical bits losing energy along the way.
In theory, yes. But, as the sources are pretty careful to explain, putting a motor right out there at the wheel also brings some serious challenges you have to solve.
Like what are the big hurdles for in-wheel motors?
Well, one major one is just the environment down there. Think
Ah.
about it. The motor's constantly exposed to dust, dirt, water spray, road salt in the winter, big temperature swings.
Yeah, that sounds like a rough place for complex machinery.
It is. It's a tough neighborhood for sensitive electronics and spinning parts. So durability is a huge question mark.
How is DeepDrive tackling that, do the sources say?
They mentioned that a lot of R&D has gone into sealing these motors properly. They're working on specialized sealants and protective casings to make sure the motors are tough enough to handle those conditions day in, day out.
Okay, so sealing is one big challenge. They're working on it. What's the other main technical headache?
The other one you always hear about, especially from engineers and people who care about driving dynamics, is unsprung mass.
Unsprung mass. Okay, refresh my memory. What counts as unsprung mass?
Basically, it's all the weight in a vehicle that the suspension doesn't directly support. So everything between the road and the springs. That includes the wheels themselves, the tires, the brakes.
And parts of the suspension and steering bits. Got it.
Right, so if you stick a motor inside the wheel hub, you're adding weight directly to that unsprung category. Weight that has to bounce around with every bump and pothole without the suspension smoothing it out first.
Ah, I see. And adding weight there isn't good for handling, is it?
Generally, no. More unsprung mass can make the ride harsher, negatively affect how the car handles, how responsive the steering feels, especially on bumpy roads.
And the motor itself takes a beating from all those road shocks too, presumably.
Exactly. It's a really key engineering challenge for any in-wheel motor design. How do you add the motor without wrecking the car's ride and handling and make sure the motor survives the constant impacts?
That sounds like a fundamental problem. How do DeepDrive and partners like BMW argue against that concern?
Well, they make a couple of points based on their work so far. First, they stress that these motors were designed from the ground up to handle very high shock loads. They've been tested for robustness.
Okay, so they're built tough.
That's the claim. Second, they argue that while, yes, it does add unsprung mass, the total increase might not be as terrible as people assume. You have to remember, there's already significant weight there from the wheel, the big tire, the heavy brake components.
Right, it's not like you're starting from zero weight there.
Exactly. So it's a percentage increase on top of what's already there, not necessarily doubling the unsprung weight or anything that drastic.
So it adds weight, yes, but maybe it's within limits that engineers can manage through suspension tuning and other design choices.
That seems to be their argument. But look, the real proof is in the pudding, right? And the sources are clear. The critical phase is happening now. Those road tests with BMW.
Right, putting them in actual cars on real roads.
That's where they'll find out for sure. They're installing different versions, testing the handling, the durability, the whole driving experience under real-world conditions. That's the make-or-break testing.
It sounds like they're definitely past the purely theoretical stage then. So how close is this tech to actually appearing in cars you or I could buy? What's the market status?
It seems pretty advanced, actually, mostly because they've managed to get serious buy-in and partnerships. BMW being a key partner and investor is a really strong signal.
Yeah, BMW doesn't usually throw money at vaporware. Their involvement suggests they think this is credible tech.
Absolutely. And it's not just money. BMW's been actively working with them, running those pilot projects you mentioned, and now putting the motors in their own test cars for these road trials. It really looks like they see this as a serious option for future EVs.
And it wasn't just BMW interested, was it? Didn't the sources say they're talking to lots of car makers?
Correct. DeepDrive themselves say they're working with 8 of the world's 10 largest auto manufacturers.
8 out of 10. Wow.
Yeah, when you have that kind of broad interest from the biggest players, it tells you the industry is taking this technology very seriously. They're evaluating it as a potential part of their future.
Okay, so huge industry interest. What about a timeline? When might we actually see these things rolling off production lines?
The sources give a projected timeline. Small-scale production could start by 2026.
Okay, relatively soon then.
And then large-scale production, where you'd see them in more mainstream vehicles, is targeted for around 2028. They also suggested that the central motor versions, the less radical ones, will probably hit the market first.
Right, easier to slot into existing car designs, presumably.
Probably, yeah, before the full in-wheel hub systems become common.
So, next few years for early versions, maybe wider adoption towards the end of the decade. Now, we touched on needing independent validation for those efficiency numbers. Were the sources generally optimistic or still quite skeptical?
I'd say balanced. They definitely convey the excitement and the potential, and they highlight that strong industry backing. But they also include that necessary grain of salt. You know, company projections are one thing, independent tests on production cars are another. They also made that point about the Tesla Model 3 comparison. It's relevant, but maybe not the absolute peak efficiency benchmark today.
So the potential looks very real. The industry is clearly interested. The serious testing is underway. But the final verdict is still maybe a couple of years out.
That sums it up pretty well, yeah. The fact that companies like BMW are investing heavily in doing road tests really grounds this. It feels much more likely than just some lab experiment. But those tests need to confirm the benefits work in the real world without major drawbacks, like that unsprung mass issue really impacting handling.
Okay, so let's try and pull this all together. What's the big picture takeaway here for you, thinking about where electric cars are going?
Well, if you connect all the dots, the potential for much better energy efficiency, maybe even having drivetrain losses, the significant weight savings,
A high power in a small package.
the flexibility to use it centrally or in the wheels, and maybe most importantly, that big reduction in rare earth dependence. DeepDrive's tech, it really seems to offer a very compelling package deal.
Yeah, it feels like it addresses several key EV challenges head on. The range anxiety, the cost and supply issues around materials, vehicle weight, and just design freedom for engineers.
Exactly.
Hmm.
And if this technology really delivers on its promise, and if those big car makers they're working with adopt it widely, well, it could genuinely reshape how EVs are designed, how they perform, how much they cost, and how sustainable they are to build. It's a reminder that innovation isn't just about batteries. It's also about improving how you turn that electricity into actual movement.
This deep dive definitely shows how much clever engineering is still happening on core components like the motor. It's not a solved problem. People are still finding potentially much better ways to do it.
It really does. And it highlights that there are these different paths forward for EV design, doesn't it?
Yeah, which leaves you, the listener, with a pretty interesting question to chew on, I think. As EV tech keeps evolving, which approach do you think wins out? Is it these radical new ideas, like putting motors right in the wheels, completely changing the car's layout?
Or will the main focus stay on refining the more conventional central drive systems we mostly see today, just making them ever more efficient and powerful?
Innovations like DeepDrive's really put that question front and center, don't they? Which way will the future of EV performance and design lean? Something to think about.